Hello and welcome. In this video, we're going to talk about the relationship between position, velocity, and acceleration, and how that relationship ties to derivatives. So our goal in this lesson is that I can use the relationship between position, velocity, and acceleration. Let's go ahead and jump right in. So the position function is where an object is located at an indicated time. We use s of t, x of t, y of t. These are the most common ways that you're going to see the position function written. In Algebra 2, we often talk about the position of an object along a quadratic curve. As I throw a ball up in the air, this is its given position. The velocity is the rate of change of that position. When you're driving a car, you're being given your velocity. What miles per hour are you driving? And again, rate of change in calculus means slope, which means derivative. So the velocity function is actually the derivative of the position function. So v of t, velocity, is equal to s prime of t. Something important to note, velocity has a sign element. If we are moving and we have a positive velocity, that means that we're moving right or up, depending on what type of position function we're using. If we have a negative velocity, that means that we're moving left or we're moving down. If we have no velocity at all, if the velocity is zero, then our particle or our object is at rest. And then last but not least, acceleration is the rate of change of the velocity. So the acceleration is how our rate of change is changing. So it is the derivative of the velocity function. A of t is equal to v prime of t. So let's just quickly use that relationship with this example off to the right. It says use the given information to answer the questions. We are given the position function. So to find the velocity, not the derivative of the velocity, to find the velocity function, we're going to take the derivative of the position function, and we can do that using the power rule. That's going to give us 3t squared plus 1. So if we were asked for the velocity at 1 second, we would just plug in 1, and we would get that the velocity is for whatever the units are, inches per second, miles per hour, etc. The acceleration function, we're going to take the velocity function that we just found, and we're going to take the derivative of that. So if I take the derivative of 3t squared, I'm going to get 6t, and if I take the derivative of 1, I'm going to get 0. And then just like with the velocity function, I could plug a value in. The acceleration at 1 second is 6. Whatever the units would be, meters per second squared, or inches per second squared, or miles per hour squared. We could also note that this object is moving right or up, depending on the context of the problem, since it's positive. So let's tie these things together and add a couple more vocabulary words before we jump into one big example. All right, so initial position is kind of an obvious thing to be talking about. It's where we start, so it would be the starting position at t equals 0. Unless otherwise indicated, if we were looking at what was happening from 30 minutes to an hour, then this initial position or starting position could be different. Same thing with the starting velocity. We're looking for the velocity at t equals 0, or the original velocity. The speed is the absolute value of the velocity. So if it happens to be that our velocity is -2, then our speed would be +2. You're just going to take the absolute value of the velocity that we're talking about. The net change is the ending position minus the original position. That would be our displacement. And then the total distance takes into account moving left and right. So if I started and I went back and forth and back and forth, and then I ended here, my total displacement would be 0, because at the end, I haven't traveled anywhere at all. Total distance takes into account everything that we have traveled. So all of these lengths would be added together in order to find that. So you can think about that through a lens of looking at the absolute value of the position and the distance traveled between them. So we'll look at an example of that. Let's jump into one big example about all of these different topics at once. We are going to use this position function for all of our examples from 2 to 7. So the position function is 16t to the third minus 36t squared, there should be a squared sign there, plus 24. So go ahead and pause the video and read through 2, 3, and 4 and see if you can answer any of those questions on your own, and then unpause the video and see what you got. All right, hopefully you had time to look through that. If I plug 0 into my position function, I get 24, and we're told here that we're looking at feet and seconds. So 24 feet is the initial position. What is the velocity of the object at t equals 1? So the first thing we need to do is find the velocity function, which is going to be the derivative. So 48, if I multiply 3 by 16, t to the second, minus 36 times 2 is 72, t. And then we're just going to go ahead and plug in 1. So 48 minus 72, that's going to give us that the velocity at 1 second is negative 24 feet per second. And then number 4 is asking us for the speed, so we're just going to take the absolute value of what we just found, and the speed at 1 second is 24 feet per second. All right, we're going to use the same example to look at 3 more questions. All right, number 5 asks when is the object at rest? What that really means is what t values make the velocity 0. Number 6 is asking us about when the object is moving right, which means when is the velocity positive. So if you think you can work through those on your own, I encourage you to pause the video and try. Otherwise, I'm going to work through them with you. So I'm going to take the velocity function that we already found before, which was 48t squared minus 72t. And I'm going to go ahead and set that equal to 0, and I'm going to factor out the greatest common factor with 72 and 48, which I believe is going to be 24, and I'm going to take a t out as well. So that's going to leave me with 2t minus 3. This will be 0 if t is 0, and this will be 0 if t is 3 over 2. So the object is at rest at the beginning at 0 seconds and at 3 over 2 seconds. What this is actually telling us is we start at 0. The only time it changes, or the only time it stops, is at 3 over 2 seconds. So what we can do is we can figure out what's happening between 0 and 3 over 2 seconds. Is it positive or is it negative? And then what's happening after 0 and 3 over 2 seconds. So what I want you to do is I want you to think about any nice number between 0 and 3 over 2. The first one that comes to my mind is 1. If I plug 1 into the velocity function, I need to determine if I get something positive or something negative, because that will tell me how the function is behaving between 0 and 3 over 2 seconds. So my velocity function is over here on number 5. If I plug in 1, I'm going to get 48 minus 72. 48 minus 72 is going to be a negative number. Again, I don't even care what that negative number is. I just care that it is negative. What that means is the object is moving left between 0 and 3 over 2 seconds. After 3 over 2, so we want to plug in an integer, a friendly number that's bigger than 3 over 2, like 2. We're going to look again at our velocity function here on number 5. If we plug in 2, we just need to figure out if what we're looking at is positive or negative. So if I plug in 2, I'm going to get 2 squared is 4. 4 times 48, I'm going to need to do that math off to the side. 4 times 48. This is going to be 192. And then I need to figure out what 72 times 2 is and just see if it's more or less than that. 2 times 2 is 4. 7 times 2 is 14. This is bigger. So that means we're going to have a positive value happening between 3 over 2 and on. What that means is that we're moving right as long as we're greater than 1.5 seconds. So let's formalize that. We're going to say the object moves left from 0 to 3 over 2 seconds, and right from 3 over 2 seconds on. All right, last but not least, we're going to find the total distance and the total displacement. So let's talk about displacement first. Displacement between 0 and 2 means that I'm going to plug 2 into the position function, and I'm going to plug 0 into the position function, and I'm going to subtract that. This is going to give me displacement, how far it's traveled from start to end, and it's telling us that we're starting at 0 and ending at 2. So go ahead and pause the video, plug in 2, then plug in 0, and subtract those 2 values. All right, so hopefully you gave yourself some time to do that math. If we plug in 2, we get 8. If we plug in 0, which we actually already did, we found the initial position on question 2, we get 24. So S of 2 minus S of 0 is going to give us our total displacement, which is 8 minus 24, or negative 16. So the object ended 16 feet left, that's what the negative means, left of where it started. Now let's talk about total displacement. Now let's talk about total distance. And I need some more room to work, so I'm going to erase my work in number 6 so that I can do total distance in that space. All right, here we go. When we're looking at total distance over the same interval, so we're still looking from 0 to 2, we need to take into account all directional changes. So what we just figured out already is that S of 0 is 24, and we know that S of 2, when we're stopping, is, what do we figure out S of 2 is? S of 2 is 8. Now, the only other thing that we know is that at 3 over 2, we change directions. So what we talked about when we did number 5 was that we could figure out where we were changing directions, where the particle was at rest, and on number 6, we figured out where it was moving left and right. So we know that it changes directions at x equals 3 over 2, or at t equals 3 over 2. So let's go ahead and plug in 3 over 2, and I know this fraction math is not going to be your favorite, but we're going to go ahead and do it anyways. 3 over 2 cubed minus 36 times 3 over 2 plus 24, 3 over 2 squared. So go ahead and simplify this out, and then unpause the video and see if we got the same value. So there I am showing my fraction work for evaluating at 3 over 2, and I get negative 3. So the total distance is going to be how far are we traveling from 24 to negative 3. So thinking about a number line, if I'm at positive 24 and I'm traveling to negative 3, how far have I gone? Well, I went 24 to get back to 0, and then I went 3 more. So I've traveled 27 feet over that period. How far am I traveling from negative 3 if I'm going back up to negative 8? Well, I'm going to go 3 to get to 0 and then 8 more. So I'm going 11 feet. So our total distance traveled is just going to be what I get when I add those two together. So the total distance traveled is going to be 38 feet. So displacement doesn't take into account what's happening if we're moving left or right. It's just how far are we at the end from where we began. Distance is like your car, and it's counting every mile that you travel, whether it's forward, backward, left, or right. All right, let's go ahead and wrap up this video. Our goal in this video was to be able to use the relationship between position, velocity, and acceleration, and how derivatives relate those three together to find different quantities related to a function, that is maybe a particle or an object moving along a curve. So please go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.